Elden Ring is coming out soon. God of War came out last month. And this is the year that gaming is going to make a huge comeback. I do not have any money, and I need it. So I'm hoping that these videos are going to convince at least some of you that I teach chemistry really well, or biology for that matter, and convinces some of you to join my classes, and hopefully helps me pay for those games. So let's get to it. Organic chemistry is the study of hydrocarbons in a way. It has other elements attached to it, but we're going to start off with hydrocarbons. So what exactly are hydrocarbons? Hydrocarbons are compounds that contain carbon and hydrogen only. Give me a second. So the only things that are going to be there is hydrogen and carbon. So an example of a hydrocarbon is going to be methane, CH4. It's going to be ethane, C2H6, or something like this, C2H4. Now, how does a hydrocarbon form? Each carbon atom has 4 outer electrons. The outer electrons each outer electron wants to bond with one other substance, at least one other substance, in order to form a full outer shell. So what I mean by that is, there is a carbon atom over here. It has 4 outer electrons. If it is going to bond with hydrogen atoms only, it is going to bond with 1 hydrogen, 2 hydrogen, 3 hydrogen, and 4 hydrogen, thus leading to CH4. So we can say each carbon atom has 4 hands. The same thing happens over here. This carbon is attached to 1 hand, 2 hands, 3 hands, 4 hands. This carbon is attached to 1 hand, 2 hands, 3 hands, 4 hands. So every single one of these are going to have this condition fulfilled, where 1 carbon atom bonds with 4 other people, regardless of whether they're hydrogen or carbon. In the case of a double bond, 1 double bond is equal to 2 hands. So this carbon atom is already bonded with 2 hands, 1, 2, 3, this is 1 hydrogen atom, and 4, another hydrogen atom. Same happens with this guy, 1 bond, 2 bond, 3rd and 4th bond together. These guys are called hydrocarbons. Now, there are saturated hydrocarbons and unsaturated hydrocarbons. So saturated hydrocarbons are the ones that contain carbon-carbon single bonds only. So there is going to be this, for example. This is going to be a saturated hydrocarbon, where every single empty hand is filled up with a hydrogen atom. This is an example of a propane. No matter how long the chain is, as long as there are nothing but carbon-carbon single bonds, it is going to be called a saturated hydrocarbon. Unsaturated hydrocarbons contain at least 1 carbon-carbon double bond. They can have more, but the minimum requirement is that they need to have at least 1. So for example, this guy is going to be considered to be an unsaturated hydrocarbon. This is going to be C4H8, where these carbon atoms are going to all have 4 hands, but these 2 guys are going to be bonded by a double bond. If there are more double bonds, it is going to be called a polyunsaturated hydrocarbon. And if it is going to just have this 1 double bond, it can be called a monounsaturated hydrocarbon. So how do we name these guys? We name them depending on the number of carbon atoms that they have. So let's first start off with what the saturated hydrocarbons are called. Saturated are the ones that only have carbon-carbon single bonds. So these guys are called alkanes. And the ones that have carbon-carbon double bonds, at least 1, these guys are going to be called alkenes. There's another guy that has a carbon-carbon triple bond. This is called an alkyne, but it is out of the scope of our syllabus for now, so we're not going to talk about this one. So alkanes and alkenes it is. So let's talk about alkanes, or all hydrocarbons for that matter. The prefix is a name that comes before. So at this, we get a prefix at the start. The prefix is going to be meth, which we all know about, eth, prop, bute, pent, hex, hept, oct, non, and zec. If you want me to enlarge it, this is what it is. So if there is only one carbon in the chain, it is going to be called meth. Not the one that we are thinking of, but something similar. So this is going to be called a meth. Since it has no carbon-carbon double bonds and only hydrogen atoms, it is an alkane. Alkanes end in A-N-E. So this guy is going to be called methane. If I increase the number of carbon atoms, let's make it 2. So carbon, sorry about that. Carbon, hydrogen, 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 hydrogen. This guy is going to be called ethane, as it has 2 carbon atoms and no carbon-carbon double bonds. Every other guy over here is a hydrogen atom. I am terribly sorry for my awful handwriting. I apologize in advance. So this sequence is going to continue. 3 carbon atoms in the chain means it's a propane. 4 carbon atoms butane, 5 carbon pentane, 6 carbon hexane, and so on. The list is right over here. If it has at least 1 double bond, we are going to call it an alkene. So C double bond C, it has only 2 carbon atoms, so this is going to be called ethene. Similarly, if I increase the number of carbon atoms, let's extend it a bit, we are going to have a propene. Extend it even further, and then we are going to have a butene. And this chain can increase as much as it wants. The naming from butene and onwards, there's going to be a bit of complication over here. We are going to touch on that a bit later. But in the same concept, as long as there is going to be 1 double bond, then the names are going to be ethene, propene, butene, pentene, hexene, and so on. Methane does not exist because 1 carbon atom cannot form a double bond, as there are no other carbon atoms to form a double bond with. So we start off with ethenes for alkenes. So these are the suffixes that we care about. For now, there are a lot more. The suffixes include alcohols, carboxylic acid, aldehydes, ketones, all that sort of stuff. We are going to touch on all of these factors later on in this series, but for now we're going to keep it as simple as possible. Now, how are we going to show a hydrocarbon? How are we going to represent it, or any organic compound for that matter? The first way we can show it is the empirical formula, which is the simplest ratio of the atoms that are present in the molecule. So how does that work? So imagine a scenario where we have 4 carbon atoms, 1, 2, 3, 4. Each carbon is going to form 4 bonds, as it has 4 hands. So each carbon atom is going to be filled with hydrogen atoms. The empty hands are going to be filled with hydrogen atoms. So if I count it, 1, 2, 3, 4, this is C4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is H10. This is going to be C4H10. The ratio of carbon is to hydrogen is 4:10. If I simplify it, this is going to turn into 2:5. So the final answer is going to be C2H5. This is the empirical formula. If I go on to the molecular formula is going to be the exact number of atoms that are present in the molecule. So for butane, the molecular formula is going to be C4H10, the exact number of carbon atoms and the number of hydrogen atoms that are present in the molecule. If I consider the structural formula, it is going to be how the carbon atoms are arranged, which carbon atom is attached to whom. So if I draw butane, once again, I have no idea why I erased it. This is the structure of butane, hydrogen atoms everywhere. I'm just going to keep it like this. I assume everyone understands that what I'm doing over here. So the empty ends are all hydrogen atom. Alright, let me just draw it out. So we have CH3. So we write down CH3. CH2, we write down CH2, CH2, we write down CH2, CH3. So we write down CH3. This is going to be our structural formula for butane. CH3, CH2, CH2, CH3. This is going to help us immensely if there are any branches in the hydrocarbon that I just have. So most for the cases that we have talked about so far, all of these guys were straight chains. We are going to get into isomerism soon. That is a different topic. But for now, let's just see that there are some compounds that form branches. So we have these guys over here. The naming is going to get complicated pretty soon, so I will suggest that you guys buckle up. But for our intents and purposes, this guy is going to have a CH3 over here and a CH3 over here. So two CH3 molecules are attached to one carbon atom. So how are we going to write this one? CH3. This guy is attached to a CH as it is, and two CH3 molecules. So we can say CH3 in a bracket. I know that the bracket is hard to read since carbon and the bracket opening looks like the same thing, and ended off with CH3 at the end. This is going to be the structural formula for this particular compound. We are going to name it 2-methylpropane. We are going to understand how the name came later on. The last thing is going to be displate formula, the second to last. There is one more. The displate formula shows the exact structure that we've been drawing so far. So it gives us all of the information in a displayed manner. All the bonds in the molecule are shown. So we have this structure. This will be the displayed formula for butane. All the bonds have been shown. The last thing we're going to have is the skeletal formula. The skeletal formula basically gets rid of all the carbon atoms and all the hydrogen atoms and replaces them with stick figures. Now what does that mean? So in this scenario, we're going to have butane once again. So one carbon atom, let's start over here, bonds to another carbon atom, let's end over here. So two carbon atoms are already present, three carbon atoms, and four carbon atoms. That is the number of carbon atoms that butane has. So each single dot over here represents a carbon atom. The dots don't necessarily need to be there. It is just me putting them there so that you guys understand. We just assume that the empty hands of carbon, so this guy is already bonded with two people, so it must have two empty hands. We just assume that the empty hands are going to be attached to hydrogen atoms. So unless we specify that there is something different over here, it is going to be hydrogen atoms. Why did this show up? I have absolutely no clue. Alright. So this is the skeletal formula for butane. 1, 2, 3, 4. Imagine a scenario where we have a butanol that is an OH group. You might not understand it now, you'll understand it later. Just say that there is something extra attached to this particular carbon other than hydrogen. So if it is other than hydrogen, we are going to specify it. The fourth carbon now has an OH group attached to it instead of a hydrogen atom. This is how we draw the skeletal formula. In case of alkenes, if it were a butene, the butene can have a double bond over here. So we would draw it like this. We would draw the same thing, start off with 1, 2, 3, 4. But since there is a double bond between the first and second carbon, we just draw this. And this indicates the presence of the double bond. This is the skeletal formula for the hydrocarbons that we have drawn so far. Now let's get to what the structure of methane looks like. The structure of methane is going to be, sorry, I don't want to write anything down. So the structure of methane is going to be CH4. So what do we have over here? there is going to be a hydrogen, a hydrogen, a hydrogen, a hydrogen. The bond angle is going to be 109.5 degree. One carbon atom has formed 4 bonds, so it has 4 bond pairs and 0 lone pairs. Now, if you don't understand what these particular terms mean, these have been covered in a previous chapter in chemistry, but for our purposes, we just want to know since carbon atoms form 4 bonds each, so all of these pairs of electrons, where one hydrogen is giving one electron and the carbon is giving the other electron, so these are pairs of electrons, all these pairs are going to be bond pairs. When there are 4 bond pairs in an atom, the bond angle is going to be 109.5 degree. Now, what is this wedge and what is this dotted line? All these methane atoms are 3D structured, which means that they are not in just one plane. When we draw anything on a piece of paper, we can only draw the 2D model, but there is a significant amount of more that is going on over here. So the wedge indicates that there is a bond that is coming out of the plane. So imagine you're sitting in front of your screen and there is a hydrogen atom that is coming out of your screen, and the dotted line indicates that there is a hydrogen atom that is going into the screen or going behind the screen. The hydrogen atoms that are just normal straight lines, those are the hydrogen atoms that are stuck to the screen. So it is like a tripod stand with a hydrogen that is at the top and 3 legs at the bottom, where the 3 legs are all in 3 different planes, if that makes sense to you guys. So this is the structure of an alkane. The same structure is going to happen for any other type of alkane as well. So imagine a scenario where you have a propane and you're considering this guy. You're wondering what the shape of this guy is going to be. So imagine all these guys to be just one group, CH3, CH3. So there are still 4 bond pairs. So the carbon atom is going to look like this. There is going to be a wedge bond over here. We call this the wedge bond. There is the dotted line over here, H, and there is the normal plain bond over here, which is the CH3, and we have drawn propane successfully. The bond angle is still going to be 109.5 degrees. Now let's replace this with alkenes. What is going to happen for them? Now alkenes have a double bond. So if I imagine the scenario of ethene and I look at it from the first carbon's perspective, we are going to have 2 hydrogen atoms and 1 CH3 atom molecule. So carbon, hydrogen, hydrogen, and CH3. The double bond acts as if it is just a single bond. It does not have any extra repulsion. It is going to just act like a single hand. The hands are going to try and spread out as much as possible. So the bond angle between them is going to be 120 degrees. They only have 3 bond pairs and 0 lone pairs. So when it comes to a carbon atom that is bonded with another carbon atom by a double bond, there are going to be 3 bond pairs and 0 lone pairs. The bond angle is going to be 120 degrees. For an alkane, even for an alkene, as long as the carbon atom has 4 substances bonded to it, it is going to be tetrahedral, and it is going to have a bond angle of 109.5 or 109, whatever you want to say. The range is acceptable. Having done all of that, let's get to a homologous series. What is a homologous series? Now we have talked about alkanes, we have talked about alkenes. We are going to be talking about alcohols, carboxylic acids, aldehydes, and ketones as well. What do these things mean? The alkanes all have similar properties. The alkenes all have similar properties. The alcohols all have similar properties. These guys are called a homologous series. They're very similar to the groups that are present in the periodic table. So what is a homologous series? They're all going to have a few properties that are going to be in common. First one being they have the same general formula. If I look at an alkane, the first one is CH4. I'm sorry that I'm writing into other pieces of material. Then there is going to be C2H6. and then there is going to be C3H8. Every single one of these guys, CH4, C2H6, and C3H8, they can all be expressed by the general formula CnH2n plus 2. This means that if there is one carbon atom, the number of hydrogen atoms is going to be 2 into 1 plus 2, which is 4. If there are 2 carbon atoms, the number of hydrogen atoms is going to be 2 into 2 plus 2, that is 6. So this matches CH4, C2H6. If there are 3 carbon atoms, the number of hydrogen atoms is going to be 8. So we have CH4, C2H6, and C3H8. This is the general formula of the alkanes. For the functional groups, imagine an alkene. The alkene is going to have at least one of these double bonds. C2H4 is going to have one double bond. C3H6 is going to have one double bond. C4H8 is going to have one double bond. So all of these are going to have this one double bond. This is going to be the functional group that is present in all of them. They all have similar chemical properties. Because of the functional group determines what sort of chemical reactions they're going to take part in. Their physical properties follow a pattern. All alkanes, as the number of carbon atoms increases, their melting and boiling points increases. So they have similar physical trends down the group. They become solids as we go down the group. Each member of the series differs from the next by CH2. CH4, the next member is C2H6. There is one extra carbon over here. From 4 to 6, there are 2 extra hydrogen atoms over here. So they differ by CH2. C2H6 to C3H8, one extra carbon over here, 2 extra hydrogen atoms over here, differs by CH2. So the difference is always going to be CH2 from one carbon to the next. These are the properties of our homologous series. Moving on to the types of bonding in hydrocarbons, there are going to be 2 types of bonds. The one is going to be sigma bond and the other pi bonds. Now, carbon atoms have the electronic configuration of 1s2, 2s2, 2p2. This is a 6 carbon atom. Now, the p orbitals are going to get involved when we want to create a bond. Now, that is not entirely true. The s orbitals get involved as well. There is this thing called hybridization, but we are going to ignore that for now. We are going to simplify things. So imagine the p orbitals are getting into a bond. When there is a sigma bond, the p orbitals interact head on. This means that there is a large area where these bonds interact. The heads are spherical, which means they can rotate as much as they want to. And these are going to take a large amount of energy to break. So sigma bonds are stronger. They can rotate about a fixed position. And one sigma bond is present in all carbon-carbon bonds. So all single bonds are going to have a sigma bond. All double bonds are going to have a sigma bond. All triple bonds are going to have a sigma bond. In contrast, the pi bonds are bonds that happen side to side between the p orbitals. The p orbitals are dumbbell shaped. So imagine the 2 dumbbells interacting side to side. There is very little contact at these 2 points. If you try to rotate this bond, imagine 2 pieces are being like 2 rings are stuck. They're not spherical. You're trying to rotate one this side, this p orbital clockwise. The bond is immediately going to break. So this bond is going to be rigid and not allow any rotation about its axis. So it is rigid. It is not as strong as the sigma bonds, and it is only present in bonds where there are multiple bonds present. So carbon-carbon double bonds, carbon-carbon triple bonds. If there are quadruple bonds, they will be present there as well. So this is the idea where pi bonds are side-to-side interactions between 2 pi orbitals, p orbitals, and sigma bonds are face-to-face interactions between 2 s or p orbitals. S orbitals do not form pi bonds because they are spherical, so there is no such thing as a side-to-side interaction in s bonds, s orbitals. So what is a hybrid? When the carbon atoms want to form a bond, all 4 electrons are going to want a partner. Since carbon atoms need 8 outer shells, they only have 4. Each of these electrons are going to want to form a partner. Now the problem with that idea is that the outer electrons of carbon are in 2 different energy levels, 2s2 and 2p2. S orbitals have a much lower energy level than the p2 orbitals. The higher the energy level is going to be, the more willing they are going to be to react. So s orbital electrons are going to have a harder time to react than the p orbital electrons. So they are not all in the same energy level, and this is going to make it harder for them to react. So what the carbon atom wants to do is kind of bring these 2 orbitals in the middle. So the s orbital adopts some p properties and the p orbital adopts some s properties. They interact together to form a hybrid. This is called an sp hybrid. So imagine the s orbital and the p orbital gets married, and once you get married, you obviously start looking like each other. So s orbital starts to look like p orbital a bit, or vice versa. The p orbital starts to look like the s orbital a bit. So either ways, they now look like each other. The p orbital used to have a beautiful dumbbell shape. The s orbital used to have an uniform, steady spherical shape. Now they just have these distorted images of their previous selves where they have homogenized into one. So this is the sp hybrid. This we call the sp3 hybrid, where the s and p, we call it the sp3 hybrid. For alkanes only, we call it the sp3 hybrid. So we're going to skip over this a bit. sp3 hybrids for alkanes. sp2 hybrids are present in alkenes. sp hybrids are present in alkynes. What do these hybrids mean? So imagine these to be the percentage of involvement of each of the orbital. So p has 3 involvement, s has 1 involvement. So p is going to have 75% of the properties. S is only going to contribute 25% of the properties. So the final hybrid is going to be 75% P property and 25% S property. For sp2 hybrids, P contributes 2 parts of its property, S contributes 1 part of the hybrid property. So it is going to be 67% P property and 33% S property. sp hybrid, there is 1 S property and there is 1 P property. The S contributes 50%, so this is 50% S and 50% P. So we are reaching a happy middle ground where the energy level of the hybrids fall somewhere in between. So the S orbitals are at the bottom, the P orbitals are at the top, and the sp hybrids are somewhere in between the two. So S, P, sp3, sp2, sp. This is the direction of energy level. So P having the most energy and S having the least energy. The next class is going to be on isomerism. I'm hoping this class helped you out somewhat. The series is going to continue. We're going to try and complete all of AS chemistry, both for Edexcel and for Cambridge. There is a lot of overlap between your topics, so there is no problems whatsoever when it comes to trying to follow along. I thank you for your time. If you had the patience to actually sit through this, goodbye. See you next time. Allah Hafiz.